Let's now investigate the security of our position verification protocol. We have seen that if Waldo and Wenda share an arbitrary amount of entanglement, then there exists an attack. So we can certainly hope to achieve security only if the entanglement is limited. In this video, let's examine security if Waldo and Wenda share no entanglement at all, no shared states of any kind. In the lecture notes, you can find pointers to a more general proof, which is a small twist on what we will discuss here, that achieves security even if they share a little bit of entanglement. To think about the security of this protocol, let's recall some of the tricks that we've learned throughout this lecture series. These tricks are really quite universal, and I hope you will use them as a toolbox in designing and analyzing your own protocols. The first trick that I want to remind you of is the formulation of the tripartite guessing game, which captured the trade-off between uncertainty in quantum mechanics and the monogamy of entanglement. Here we will think of it as a game that Alice plays against Wenda and Waldo. The state shared by the three of them is allowed to be completely arbitrary. So Alice has a qubit A, but W1 and W2 can be anything. According to her input theta, Alice will measure her qubit in either the standard basis if theta is 0 or in a Hadamard basis if theta is 1. This gives her one bit of classical measurement outcome, which I will call XA. Of course, we have no idea what measurements Wenda and Waldo will perform. They will make an arbitrary measurement that could depend on the basis theta. From their measurements, they get two outcomes, which I will call XW1 and XW2. In our uncertainty game, Wenda and Waldo won if and only if they both managed to guess XA. In other words, that the guess of Waldo XW1 and the guess of Wenda XW2 are both equal to XA. As we saw earlier, the maximum probability maximized over all possible states and measurements that Wenda and Waldo might perform was roughly 0.85. Let's keep this guessing game in mind. Another trick that we've used repeatedly is the analysis of protocols by purification. We imagine that instead of sending BP84 states, so X in the basis theta, instead Alice prepares EPR pairs. From each pair, she keeps the first qubit, A, and she sends the second qubit to Waldo. She might, of course, keep that qubit all the way until Waldo returns the message. So at this point, she might still have the qubit A. The outcome of Alice's measurement, if she now measures A in the basis theta, will define the bit X. Of course, if Alice measures only at the end, there is no X determined until then, but she can communicate with Bob to exchange X and check on Waldo afterwards. So let's see how we can use these two tricks to prove security. I will focus only on one round, so n is 1, but the argument is the same for larger n. Let's first see what an attack by Waldo and Wenda actually looks like. So Alice and Bob share theta as before. Alice prepares the EPR pair and sends qubit Q to Waldo. Of course, now if Waldo is dishonest, we have no idea what he will do. However, Waldo is quantum. He cannot do things which are not permitted by nature. So he will use his quantum computer to do some processing on the incoming qubit and potentially some other quantum system. Let me divide the resulting quantum system in two parts, which I will call L1 and L2. I'll split it up in two parts because in the most general form, Waldo will now send a message, namely L2, to Wenda. Of course, part of that message could also be classical, but it can definitely also be quantum. So what can Wenda do? Upon receiving theta, Wenda can also fire up her quantum computer, do some processing, resulting in a quantum system D1 and D2. She will send D2 as well as the basis theta to Waldo. So at this point in time, Waldo has theta, D2 and L1. Let me call D2 and L1 together W1. Wenda also has theta, as well as L2 from Waldo and D1 which she keeps. Let me call D1 and L2 together W2. Waldo and Wenda now have to send classical bits to Alice and Bob. Let me call the bit of Waldo XW1 and the one of Wenda XW2. So in this purified version of our protocol, Alice will now go and measure A in the basis theta. This gives her a bit X or XA. The check that Alice and Bob perform in this protocol is to check whether both XW1 and XW2 are equal to XA. If no, they accuse Waldo of cheating. So what is the probability that Waldo and Wenda can trick Alice and Bob in just one round of the protocol? The idea is that we can map their attack onto the guessing game. To see how, let's look at the situation at this point in time. Alice measures theta to get XA. And Waldo measures W1 to get XW1, and Wenda measures W2 in order to get XW2. Waldo and Wenda manage to trick Alice and Bob precisely if XA is equal to W1 and XA is equal to W2. So we are indeed back to the guessing game. To make this absolutely clear, let me draw here again the situation as it is mapped onto the guessing game. We have just Alice, Waldo, and Wenda. Waldo has W1, Wenda has W2. And the rules of the checking is exactly the rules of the guessing game. Or if I write it in the familiar form of the guessing game, Alice has at the end her qubit A, which she measures in the basis theta to get XA. Bob has a qubit or larger quantum system W1. He performs some arbitrary measurement, getting XW1. Wenda has some quantum system W2, performing an arbitrary measurement to get XW2. And this is precisely the check that Alice and Bob performed. So the rules of the check of the guessing game are the same as the check in our position verification protocol. So now we know already from the guessing game that Waldo and Wenda can only cheat with probability p roughly 0.85. Of course, you might say 0.85 is still pretty large. There's a large chance that Alice and Bob get cheated. So how can we make this probability smaller? Again, we will resort to our usual bag of tricks. Let's not just use n equals 1, Alice making only one EPR pair, but let's do this many times. It is not obvious, of course, in the guessing game that Waldo and Wenda cannot do better if they attack all n rounds together, instead of using the attack for just a single round that we've just described. In the quantum case, this is actually usually not easy to show, since the attacker's strategy may of course use entanglement across all n rounds. However, in this case, it turns out that Waldo and Wenda really cannot do any better than to attack the individual rounds. And the overall probability that they manage to trick Alice and Bob will scale as p to the n, where p is our 0.85. Hence, by making n large enough, Alice and Bob can get any desired confidence in Waldo's position. This analysis can also be done if Waldo and Wenda share a limited amount of entanglement. To get some intuition of why this is so, note that we saw already a few times that someone's advantage in guessing x is not increased by more than a factor related to the size of the quantum system that they might be using. Very roughly, it is this idea that allows one to establish security even if Waldo and Wenda have a little bit of entanglement. But this I will leave for you to read about.